Okay, welcome to the fourth example in the chapter of torsion. The question reads, the composite shaft consists of a bronze sleeve securely bonded to an inner steel core. The bronze sleeve has an outside diameter of 35 millimeters, an inner diameter of 25 millimeters, and a shear modulus of 45 gigapascals. The solid steel core has a diameter of 25 mm and a shear modulus of 80 gigapascals. The composite shaft is subjected to a torque of 900 Newton meters. Determine A, the maximum shear stresses in the bronze sleeve and the steel core, and B, the rotation angle of NB relative to end A. Okay, so we can start off with the information given about the bronze sleeve, right? So we can say bronze sleeve. And we can say steel core. Right, so for the bronze sleeve, we're given that it has an outside diameter, so we'll call it DBO, an outside diameter of 35 millimeters, an inside diameter of 25 millimeters, and a shear modulus of 45 gigapascals. 45 gigapascals. For the steel core, it has a diameter, it's just solid, so it has a diameter of just 25 millimeters, so it fits snug inside of the bronze sleeve, and or it's bonded, actually. It doesn't fit snug, it's bonded, right? That's important, kind of. And it has a modulus of rigidity of 80 gigapascals. Okay, one other information we're given is that this torque T that acts on both ends has a value of 900 Newton meters. And I think that's all for givens. There is one thing to note in this question, and that is that for the polar moment of inertia, for the solid steel core, it's not an issue. It's just r to the power fourth, right? Because solid cross-section. For this one, it's actually not a solid steel core. It's not solid. Like it's a hollow cross section, and the polar moment for inertia for a hollow cross section is actually pi over 2 r outer to the fourth minus r inner to the fourth. R inner to the fourth, and that's simply because it's j outer minus j inner. The polar moment of inertia outer minus the polar moment of inertia inner, and that's just pi over 2 r outer to the fourth minus pi over 2 r inner to the fourth, and then if you factor out the pi over 2, you get both to the fourth power, right? And it's not the same as this, right? Okay, wonderful stuff. So we can move on to unknowns. This question wants us to find quite a bunch of stuff, but it shouldn't be too hard. Unknowns, we want to find tau max, maximum shear stress in the bronze. We want to find tau max for the steel. And we want to find the angle of rotation of B, right, relative to A. Okay. So to start off, we have to find for these formulas, and I'll put the formulas in the corner here. Remember, T, or the angle of deformation, is equal to T L over JG, and the shear stress in torsion loading is equal to TC over J, right? If we want to start first off by finding these, we have to find the torque. We have C, we have J for both of them, right? We want to find the torque in the bronze, so TB, and we want to find the torque in the steel to then find our respective shear stress in the bronze and steel, right? So that's what we're going to do. Let's see if summing torques will work. Spoiler alert, it will not work. So we have to do some angle deformation analysis. So let's call this free body diagram, I guess. I don't know, can't think of a better name. Free body diagram. Right. If I cut a section halfway through, just right down the middle, it doesn't really matter, but if I just cut a section, most likely halfway through is better, and we'll analyze that section. Say it looks like this. And then I have the outer core, right? And the outer core is the one that's going to show, or the bronze sleeve. And then I cut it like this. And then I have my torque T, which has a value of 900 Newton meters, acting at my end. If this is my end B, this is my end B. I have my torque T acting counterclockwise at my end B. That's a bad color. It's acting counterclockwise at my end B, right? And we'll just call it 900 Newton meters for now. 900 Newton meters. Remember, if I take this section, what is my reaction torque? What is it going to be made out of? I know I'm going to have a reaction torque the other way, but this reaction torque is made up of two components, right? It's made up of the torque, of the reaction torque due to the bronze, plus the reaction torque due to the steel, right? Because we have these two components, right? So this 900 Newton meters of external torque is opposed by a reaction torque in the opposite direction, and that reaction torque is namely made up of TB and TC, or TS. Okay, if I take sum of torques and I say counterclockwise is positive, I set it equal to 0, I'm going to end up getting my first equation, which is TS plus TB is equal to 900 Newton meters. And this is my equation 1, right? I have one equation, two unknowns. I need another method to find my two unknowns because it's a statically indeterminate problem, and that is analyzing the deformation of this lovely shaft, right? So 4, deformation analysis. For this one, the analogy or the relation is fairly simple. Remember when I said this one fits snug, and then I was like, actually, no. It's firmly bonded together. Well, that wasn't just because I start like doing that philosophical stuff. It's literally because they are bonded together, right? And what does that mean? This means that if this inner core rotates by, again, let's say, I don't know, an angle of pi over 6, right, of 30 degrees, this outer core is also bonded to it. So this one will also rotate because, like, think of it as one structure, right? It'll also rotate by pi over 2. What does that mean with regard to the angle of deformation for the steel compared to the angle of deformation with the bronze? Well, that simply means that they're equal, right? If this one rotates by a specific amount, this one will also rotate by a specific amount. So the relation is fairly simple, right? It's just that the angle of deformation for the steel is equal to the angle of deformation for the bronze. And from there, I can say that TC or TL, JG, actually we have the formula in this corner for reference, right? And let me just put it in frame a bit. And let's fill out the equation for the steel first. So the steel is the inner core. So I have the torque of the steel multiplied by L. I keep it as L for now, right? Divided by J. Remember, the steel is solid, so it's just the radius. So pi over 2, in this case 12.5 mm to the 4th, multiplied by 80 times 10 to the power of 3 megapascals. Right? Beautiful stuff. And this is equal to the torque of the bronze multiplied by L. Just keep it there for now. And then this is pi over 2. The outer radius, right, for J, the outer radius minus the inner radius. So 35 mm to the power of 4 minus 25 mm to the power of 4. And then we also multiply by the modulus of rigidity. So it's 45 times 10 to the power of 3 megapascals, right? The lengths are the exact same regardless of what I'm analyzing. It will be the exact same, so I can cancel those out, right? With regard, there are like common mistakes that, okay, I'll use the exact same modulus of rigidity. Please do not do that, right? They're not the same. But with that, we can go ahead and start canceling our lengths, because as we just explained, they're the exact same, right? So we can cancel those out. And from this, we can come up with an equation, a linearly independent equation from equation 1 that represents our torques for the steel and for the bronze. And from this, you're going to get, if you isolate a bit, you're going to get that the torque of the steel is equal to, or actually, let's make this, flip it around. The torque of the bronze is equal to 1.5984 times the torque of the steel, right? And this is your equation 2. You sub into equation 1 using any of the methods you want, and from there you're going to get that the torque of the steel is going to end up equaling 346.36 Newton meters, and the torque of the bronze is going to equal 553.63 Newton meters. And beautiful. You're not done just yet. You have to find the shear stress, but that is simply just plugging in stuff to a formula, right? So the shear stress, or the maximum shear stress in this case, is equal to TS for the steel, is equal to TS multiplied by C over J. In this case, C is, if I remember correctly, which I'm not going to remember correctly, so let's cheat. It's going to end up being 12.5, right? 12.5 mm, 12.5 mm divided by your polar moment of inertia, right? So that's pi over 2, 12.5 mm to the power of 4. For the bronze, it's just a bit more difficult, or not difficult, but like it's just a bit more long, right? So TB multiplied by the C in this case. That's also a very good point. C in this case, I'm pretty sure we mentioned it before, but C in this case is not the like radius. If this is, because remember the bronze sleeve is hollow, right? It's not the distance from here to here, right? It's still the distance from the center of rotation, like the torsion, the axis that's perpendicular to your face, right? So if this is what it looks like, this is what it looks like. It's still the distance from this axis, right? From your perpendicular axis to the cross-sectional area to your outside diameter, right? So this is still your C. Do not use this right here, right? So, yeah. So in that case, it would just be 35 divided by 2, which is 17.5. So 17.5 mm divided by pi over 2. Oh, that is interesting. Over here, there's nobody to correct me, so I have to catch my own mistakes, yeah? So this is 35 and this is 25. This is incorrect. This should be 17.5 and 12.5 because it's the radius, right? It's not the diameter. $35 mm. Oh my god. 17.5 mm, 12.5 mm. Perfect stuff. So that exact same thing is going to come down here. We should have explained this as well. Yeah, we should have explained this as well before. So it's simply 17.5 mm to the power of 4 minus 12.5 mm to the power of 4. Right? From this, you're going to get that the maximum shear stress in your steel is going to be a value of 88.9 megapascals, and the maximum shear stress in your bronze sleeve is going to be a value of 112.9 megapascals, right? Beautiful stuff. So that is your answer to part A, where it wants you to find these two lovely guys. Now we want to find the deformation of this, the angular deformation of this point B relative to point A. And what does that basically mean is we're going to keep point A fixed, right? And we're going to see how much B rotates relative to A, right? Should I redraw that out? Let's just finally draw it out. So we want to find angle theta B relative to A. If we draw it out like so, it's kind of going to look like this, right? And if this is my cut, Or actually, I'm not going to have a cut, right? I'm going to make B fixed, or A fixed. Apologize. It's just so zoomed out, so it's not going to be straight. Let's say A is fixed. A fixed, right? And I want to find my deformation at point B relative to point A. So I want to find how much this rotates, right? So, and I have my torque B, right? Just to complete the diagram. So I want to see this setup. So let me just zoom in. I don't need anything else. The angle for deformation is equal to TL over JG, right? Okay. Right now, I have two options. I can either see the rotation of this steel core relative to A, or I can see the rotation of the bronze sleeve relative to A, right? What's the difference? Well, for the bronze sleeve, I would have to use TB, right? And I would have to use JB, right? And and GB and JB and GB, the shear modulus, and the polar moments of inertia for the bronze sleeve. The length will be the same. It'll be 360, I believe, millimeters, right? But if I'm using the steel core, I'm going to use everything that has to do with the steel core. The question is, why am I not using this 900 Newton meter torque as my torque at B? Well, this 900 meter torque, as we've basically derived here, it doesn't just represent the rotation of like if you had a solid shaft, then yes, you could do that. And if it was one fluid material, you could do that. But this is two separate materials. So let's say, okay, fine, put 900 in this equation. What are you going to use as G? And what are you going to use as J? Right? Are you going to use the bronze sleeve? Or are you going to use the steel core? Right? Those are the questions that you need to ask. But even if you look at it, it makes sense, right? Even if I were to somehow find the rotation using 900, wouldn't, since everything's bonded fluidly together, wouldn't the rotation of just this specific cross-section be the same as this entire cross-section, right? So just for example, let's do the bronze, actually no, let's do the steel, this inner steel core, right? So I can say TS, TS, RGS, and then JS, right? And it's easier as well because the polar moment of inertia is smaller. I think we got for TS a value of 346.36 Newton meters multiplied by the length, 360 millimeters, right, from B to C, or from B to A, divided by the polar moment of inertia, which is 12.5 millimeters to the fourth, multiplied by my shear modulus. Once you do this, you're going to get a rotation or an angle of deformation of 0.04064 radians. And these three guys are your answers to this question.